Good morning, everyone. Hope you're all well and doing okay with the last week of semester. So, welcome to our last class for human-computer interaction. We're going to spend a couple minutes this morning first talking about the final project, which, just as a reminder, is going to be bright and early next Tuesday morning. We will then finish the course by discussing cyborg technology. I think we have more than enough material in today's lecture and lecture 27 that we will not get to augmented reality. For those that are interested in that technology, please do have a look at those lecture notes at your leisure. Okay, so let's talk about the final project. Just as a reminder, you're currently working on interim video 3, the final one, which will be due the night before our final project presentations. So what I would like you to do and ask all of you to do is to please make sure to read the final project document. Everything you need to, all the remaining material that you need to submit for this project is described in this document. So please do read through this. We've talked already about the interim videos. So section 2, this one is particularly important. This is has to do with the logistics about returning your Leap Motion device. We have 60 of them that have been mailed out to all of you. We need to collect all of those back for next year's students. So one part of your homework for next week is to return the Leap Motion device to us. Here are the instructions for doing so. So by midnight next Monday, you will be printing out a shipping label that will be mailed to you. I will email each and every one of you with a shipping label as a PDF. Print it out, tape it over the shipping label on the USPS box that your Leap Motion device arrived in. I know many of you have moved back home. Some of you have moved countries. I realize this is going to be a complicated logistical process. Just bear with me. If you do not have the USPS box or you do not have your Leap Motion device, you've left them on campus, they're somewhere else, that is perfectly fine. If you cannot find the box or there is some reason why you cannot mail the Leap Motion device back to us by next Monday morning, please email the TA and we will provide alternative instructions for you. So we need proof that you've sent back the device to us by next Monday night, or you've emailed us with extenuating circumstances. Okay. If we do not see an indication that you've mailed it back, or we do not receive that an email from you, you will receive a failing grade for this course. I apologize. I don't mean to be harsh, but like I said, we need to get those devices back. Or at least we need to hear from you about other ways that we can retrieve it. And we can work that. If there's alternative plans, we can work it out, but we need to hear from you about that. Okay. All right. If you do have the box, please print out the label, put it on the USPS box, put the Leap Motion device and the cable back in the box, put that box in the USPS box, tape the box closed, and drop the box with the label on it in the mailbox. When you have done that on Monday, please indicate that you have done so in column K on the original Leap Motion sign-out spreadsheet. So you'll see in column K here, all you need to do is type in, yes, I've mailed back the device. We need that by Monday. We need that by Monday. Okay. Any questions about returning the Leap Motion box? If you don't have the box, you don't have the Leap Motion, you don't have to ask about it now. Make sure you email us by Monday. I'm sorry. Please indicate you've mailed it back, or email us that you're not able to mail it back by midnight on Tuesday. I'm sorry. Okay. I hope that's very clear. Thank you. All right, so let's talk about question. No? Okay. So let's talk about the exam period itself. Amanda, did you have a question or a comment?
Nope, I was actually waiting for you to go down to the exam period.
Okay. All right, so let's talk about the exam period itself. So again, by next Monday night, you are submitting the interim video 3. You are also submitting a URL that points to a 2.5-minute YouTube video. Okay, so this is going to be your oral presentation. During our exam period, you will be presenting your final project orally by talking over your video. I will put up the order of oral presentations exactly at 7:30 on exam day. So again, I realize it's early. Please be sure to be here right at 7:30. There will be a meeting in our team CS 228 Teams for you to join at that time. Okay. It is very important that you submit your work by Monday at midnight, because Amanda, the TA, is going to stitch all 60 oral presentation videos into a single playlist. She obviously needs your link at midnight to be able to do that. So if you do not submit the link by midnight, there are no late extensions, because we are presenting bright and early on Tuesday morning. Okay. All right, the written report. So Monday night, you're submitting interim video 1, a link to your oral presentation, and you are also uploading a PDF, which is a 3-page written document. This 3-page document is a summary of the work you've done since deliverable 10. In about 1 page, you should summarize your added functionality. In the 2nd page, you're going to describe how you had to alter your code to do so. And the 3rd page is going to be how you would have performed fair and quantitative testing of your system if we had been able to do so. As I mentioned a few times by now, we weren't able to do any testing this semester in order to respect social distancing. You might want to go back and have a look at the lecture where we talked about user testing, ways of trying to do quantitative user testing. If you do user testing against a particular non-functional requirement and you get consistently low scores, what does that tell you about your interactive system? If you get a high standard deviation on one of your testing metrics. So some people found your system very intuitive, other people found it very confusing. What does that tell you about your user, about your interactive system? So I want you to take that theoretical discussion we have and apply it to your system and describe what you would have done if you had deployed the testing system, if you had gotten these kinds of scores or these kinds of scores, if some users had found it intuitive, some had found it confusing, some found it accessible, some found it non-accessible, and so on. How would you have handled that process? I realize this is a hypothetical exercise, but this is the best we can do. Obviously, user testing is a big part of HCI, and we weren't able to do any this semester. Okay, on the 2nd page, as I mentioned, you're going to give us a summary of how you had to restructure your code. It's not very informative for you or for us if you just copy and paste code snippets directly into your written document. So instead, on the 2nd page, I want you to provide a written summary, and here's an example of what that might look like. In order to add math functionality to my system, I added an additional state 4, to my program. This state was reached when the user successfully signed all 10 digits without having to see the image of the hand. They were able to do all 10 digits without scaffolding. When they did, that triggered state 4. State 4 was continued as long as the user successfully signed the answer to mathematical equations. If the user failed to do so, the code would return to state 3. This also required me to change when training and testing were called, because the KNN had to be deactivated in state 4 but reactivated in state 5, and so on and so forth. Okay, this is obviously just a hypothetical here, but this is meant to give you an idea of how we want you to describe the code restructuring required to support your added functionality. Okay, that report is also due Monday night. So Monday night you're submitting 3 different items: interim video 3, the URL that points to your 2.5-minute oral presentation, and your written report. All good so far? Questions, comments? Okay. Let's talk about the video itself. As I mentioned, it needs to be 2.5 seconds long. There's slightly different ways you can do this, but here's my suggestion. In the first 30 seconds, you put up in the video a stationary Google slide in which you summarize the functionality you added to your system. You might want to include some static screenshots here. Spend about 30 seconds telling us about the functionality that you added. I would then include about a 1-minute video demonstration of you exercising all the functionality that you added to your system. And then in the final minute, again, you might flash up a slide or a simple animation documenting your plans for fair and quantitative user testing if you had been able to do so. Again, we weren't able to do so. So this is more or less a reflection of your written document as well. Okay, so that's 2 minutes and 30 seconds. It goes pretty quickly. Okay, if you have video editing software, please feel free to use that to make your 2.5 minute video. If not, you can create your video in the following way. Set a timer for 30 seconds with your phone, shoot 30 seconds video of your stationary slide, upload that to YouTube. Do the same thing, use your, as you've been doing all along, use your phone to capture about a minute of you demonstrating all the functionality in your system. Make sure we can see your hand, make sure we can see your screen. That gives you an additional minute, upload that. And then finally, capture another minute of your static slide documenting your user testing for about a minute. Upload that to YouTube, stitch that together into a single playlist. Play the playlist back and shoot that 2.5 minute playlist with your phone. Okay, kind of hacky, but again, that's a way to make a 2.5 minute video without requiring any video editing software. Upload the resulting 2.5 minute video to YouTube. Make sure that YouTube is unlisted or public and submit the link to YouTube. Okay, we will not remove any points for poor video quality. However, we do need to be able to see, as long as we can see what you are attempting to show us in the video. Make sense? Okay. Okay, and then, yeah, submit that URL to Blackboard at 11:59 p.m. on Monday. Okay. All right, so then what happens on Tuesday morning? On Tuesday morning, before 7:30 a.m. on Tuesday morning, Amanda is going to stitch all 60 videos together into one long YouTube playlist. We will embed 3 10-minute breaks in there with 60 2.5-minute videos and 2 or 3 10-minute breaks. That'll cover the 2 hours and 45 minutes that we have for the exam period. Okay. I will post the presentation schedule right at 7:30 a.m. At 7:30 a.m., I will start the YouTube playlist and we will share I will share my screen. So we'll all be back here in Teams. We will all be collectively watching a 2 hour and 45 minute YouTube playlist. Okay, according to the schedule, you will see when your video is going to start. When your video starts, unmute yourself in Teams and you are going to talk over your slides. So this is important. Your slides should be completely silent, no audio at all. You are going to be narrating your video live. When you finish narrating over your video, please mute yourself again. If you are still speaking when your 2 minutes and 30 second video finishes, I will mute you and the next speaker will start speaking. So there is no break between one video and the next. That's the only way we can get through 60 presentations in 2 hours and 45 minutes. Okay. Giving an oral presentation like this, especially in Teams, can be a little bit challenging. So please practice, practice, practice. It's only a 2.5 minute presentation. So in about 30 minutes, you should be able to practice over 10 times. You want to make sure you have your presentation down pat. There is no opportunity to pause, rephrase, and carry on because the video is going to continue on without you. Okay, so practice, practice, practice. We need them to be exactly 2.5 minutes so that we don't go over our 2 hours and 45 minutes. So if your video is shorter or longer than 2.5 minutes, points will be deducted. If your video is 2 minutes and 31 seconds or 2 minutes and 29 seconds, that's fine. But even 10 seconds one way or the other, we're gonna get off schedule. So please keep it to 2 minutes and 30 seconds. You will be graded for the clarity of your presentation. So can we see everything we need to see in your video? And can we hear everything we need to hear in your narration? We'll grade your ability to verbally convey a summary of your new functionality. So if we can't understand what you're describing, that's a problem. A clear description of what that functionality is while it is being shown in the video, and the timing of your presentation. So as you are demonstrating your functionality in the video, you can be narrating it saying, as you can see, I'm now signing the answer to 3 + 4. Now you can see that I'm failing to sign the answer to the equation correctly. So the system is now backing up to presenting single digits. Yeah? Okay, so real-time narration. Okay, I think that's all I have to say about the final presentation. Again, that was a lot of information, so please read through this carefully before next week and make sure that you're submitting everything that we've asked for and that you're ready to go right at 7:30 Tuesday morning. Yes, Amanda.
This is what I was waiting for. I just really wanted to emphasize for everyone that as far as submitting the videos, late submissions will not be accepted. Throughout the semester, we've been a little lenient. If you submitted at like 12:30, we were a little lenient on grading there. But for this, I need to be able to put together this playlist. And because the final's at 7:30, I would like to be able to get to bed as soon as possible. So we really won't be accepting late assignments. You need to submit it by midnight so that I can get to work stitching together the playlist. Thank you.
Yes, thank you, Amanda. So Amanda also has exams and other responsibilities, so absolutely no exceptions if the video is submitted after midnight. Remember to make sure that the video is either unlisted or public on YouTube. Any other questions or comments before we move on? No? Okay. All right, so again, we have reached the end of the semester. We've covered a lot of ground in this class. Just as a very, very quick recap, at the very beginning of the course, we had an overview of what HCI is about. We spent a lot of time throughout the course talking about focusing not on what a technology can do, but on what someone or someone's would like to do with that technology. We spent a lot of time in the class talking about design. How does designing an interactive system, how is it similar or how is it different from designing technologies in other domains like engineering, software engineering, architecture, and so on. We talked about the HCI design process in which user testing is central. I would suggest you go back and have a look at lectures 7 and 8 when you get to thinking about user testing for your system, even though the user testing is going to be hypothetical. We talked about the human element in HCI. What are some of the features or not bugs, but what's the word I'm looking for? Idiosyncrasies of human cognition, the human visual sense. The brain is a prediction machine. Your brain makes predictions about what happens when you push against the world. Then we spent a fair bit of time looking outward. So what are the challenges and opportunities of stitching interactive technology into the physical world, where that technology is sensing and acting in the world similarly to the way that humans push against the world and observe how the world pushes back. The week before that, we started in on looking inward. So not only is technology invading and colonizing our world, but we are also increasingly entering virtual worlds, and that raises particular challenges and opportunities. We talked about virtual reality, in which we try and replace the physical world with a virtual world, but that virtual world tries as best it can to provide expected sensory repercussions to head motion, whole body motion, hand motion, and so on. Finally, today we're going to finish our discussion of technologies, interactive technologies that sit on the skin or under the skin. So we got to Norbert Wiener last time, who way back in the 1940s envisioned interactive technology as helping to mediate the human feedback loop, where the human pushes against the world and observes how the world pushes back. But what happens if for a particular human that feedback loop is disrupted in some way, where some part of that feedback loop is no longer working? So what happens if the neural pathways that go from our eyes or our ears to our brain is disrupted? Can we replace those sensory pathways with a cybernetic device which captures physical phenomena arriving at our sense organs and passes it directly to the brain? Or what happens if we implant a cybernetic device that captures motor desired motions from the brain, ideas about how we would like to act, and passes over perhaps a damaged spinal cord and provides those signals directly to our muscles? Okay, that's cybernetic technology, which we'll see a few examples today. There is another type of nervous prosthesis which leaps over not just sensory pathways or brain to muscle pathways, but leaps over sense organs altogether. So what happens if, for example, instead of functional eyes being connected to dysfunctional optic nerve, which is the connection from eyes to brain, what happens if it's the eyes themselves that are non-functional? Can a camera, for example, capture a visual signal from the real world and pass that directly into the brain, bypassing the eyes and the optic nerve altogether? Alternatively, what happens if it is not just the spinal cord that is damaged, but the muscles themselves are either absent or inactive? Can we capture a signal from the brain and instead of supplying it to the muscles, supply it to a robotic prosthetic that is able to exert force on the environment on behalf of the human wearer? This is the most recent emerging branch of human-computer interaction, which is brain-computer interaction, or BCI. Right? We are trying to mediate between the physical environment and the brain directly using cybernetic devices. Okay. So where did actual cybernetics begin? We can argue about this point, but arguably the very first Cyborg appeared in 1998. Kevin Warwick was a professor at that time at the University of Reading in UK. In the UK, the laws regarding self-experimentation are a little more relaxed than they are here in the US. Professor Warwick took it upon himself to surgically implant a radio frequency or RFID transmitter underneath his skin. RFID tags are a very common type of technology. They're very, very small, very, very lightweight, so a good candidate for something to be surgically implanted. An RFID tag can capture incoming radio waves and use the energy in those waves to supply a short burst of power to do something on the chip. So there's no battery inside an RFID tag. It captures energy from incoming radio waves and does something. In this case, the RFID tag would then send out a personalized signal to an electronic door lock or an electronic light switch so that Professor Warwick could unlock the door to his office with just holding up his hand. Okay, as you can imagine, this was a little bit of a publicity stunt. 3 years later, he implanted another device into the median nerve of his left arm, which means that that nerve was actually supplying signals from Professor Warwick's brain to this device, and this device was then sending commands to a robot hand. And Professor Warwick claimed to be able to control the robot hand just by moving his own hand. If you go and watch the video, I don't see much of a correlation between the movement of his hand and the robot hand. I think, again, a bit of a publicity stunt, but arguably one of the first cyborgs. Okay. A much more common technology these days, and definitely much more useful, is a cochlear implant. Cochlear implant is different. Is different from a hearing aid. A hearing aid assumes that the inner ear is still partly functional, and a hearing aid simply amplifies volume and supplies it to a damaged inner ear. Cochlear implants are for those that have a non-functional inner ear. It doesn't matter how loud signal you supply to the ear, nothing is getting through. How does a cochlear implant work? Well, there is a microphone that captures pressure waves corresponding to sound or speech on the outside of the wearer's skull. There's a little bit of a speech processor. So even at this early stage in this technology, it is trying to filter out other sounds and supply just speech. That speech is provided to a transmitter that transmits waves wirelessly across the skull and is received by a receiver on the inside of the wearer's skull. That electrical signal that's received from the transmitter is supplied to an electrode array that you can see is surgically implanted in the spiral-shaped cochlea. An electrode array is made up of a number of electrodes. What do electrodes do? They transduce electricity into some other form. In this case, the electrode array collects impulses from the stimulator and sends them electrically, or in some cases through very high vibrations, to different parts of the auditory nerve inside the cochlea. The cochlea normally is filled with a viscous fluid, and there are very small cilia, or very small hairs on the inside of a cochlea. When pressure waves arrive at the eardrum and the eardrum vibrates, depending on the frequency, it will vibrate different parts of the cochlea, different parts of the spiral arm, which stimulates different subsets of the cilia at different places inside the cochlea. And those cilia that are detecting that vibration send electrical impulses to the auditory nerve, which is received by the brain and interpreted as speech or sound. Here, we are still stimulating different subsets of cilia, but they are being stimulated by the electrode array instead of pressure waves arriving at the eardrum. Okay. If someone is speaking to the wearer, that is speech that is being translated at the speech processor that's being transmitted to the receiver. The receiver is sending signals to different electrodes on the electrodes array, which is stimulating different subsets of cilia. This is very much like the game Broken Telephone. Because of all of these stages of translation, what is arriving inside the cochlea, and those electrical signals are quite different from the electrical signals that would have been received by the wearer if they had a functional inner ear. So the question becomes, what exactly does a deaf wearer of this technology actually hear? The answer is that every different person hears something differently. So my old doctor actually had a cochlear implant, and I was obviously curious and asked him about it. He was one of the very first to receive this technology. When he received it and it was turned on for the first time, he said it sounded like he was at a Metallica concert and he was standing in front of the amplifiers. You'll notice that there is no volume button on the cochlear implant. The cochlear implant supplies an electrical impulse that has to be interpreted by the brain in some way. Imagine wearing this device where it's basically set to maximum volume all the time. He said it was an extremely traumatic and upsetting event. He spent about 10 days at home in his room. He couldn't tolerate the slightest sound or anyone speaking. However, over the 10 days and the subsequent weeks, his brain adapted and acclimated until eventually the quote-unquote volume started to decrease and he could hear sounds at a comfortable volume. One of the most interesting aspects of cybernetic technology and human-computer interaction is that you can supply a signal that is quite different from what the brain would normally expect. And over time, the brain adapts. So you remember our discussion about virtual reality, where someone was walking in a concave dish and their foot was colliding with the concave surface of the platform earlier than their brain would have expected. You can get used to that. If you spend any time running on a treadmill, it can be very disconcerting the first time you ever use a running treadmill, but with practice, your brain becomes used to it. Same thing with cybernetic devices. Okay, so it's difficult to know exactly what any particular subject will hear after the implantation of a cochlear implant. Here, given a number of verbal descriptions from a number of users, here's what some of them reported hearing. Okay, so what you're going to hear in this video. What you're going to hear in this video is they're going to supply sounds that users have reported hearing with these multi-electrode arrays. But imagine you only have one electrode or 4 electrodes or 8 electrodes. You can think of these as low, medium, and high resolution, not for a video image, but for an auditory signal. You're going to hear a series of sounds, and those sounds correlate to a normal person speaking a single sentence, and it's going to be the same sentence repeated multiple times. Pay attention to at what point you are able to interpret exactly what the sentence is.
What kind of bait do you use to catch salmon? What kind of bait do you use to catch salmon? What kind of bait do you use to catch salmon?
What kind of bait do you use to catch salmon?
Okay. Okay, so a lot of challenges there in terms on the wearer side of adapting to the technology. Let's look at some others that are related. Here's another one. This is meant for blind subjects. This is an interesting idea where instead of trying to bypass the damaged sense organ, which in this case is the eyes, and supply it directly to the brain, instead they're going to capture a signal that is meant for the eyes and send it to the ears instead. So in this case, the wearers wear a pair of sunglasses, and in those sunglasses are implanted outward pointing cameras. So we get stereoscopic images arriving exactly from the point of view of the wearer. Those video signals are translated into a soundscape. So they're going to take the video images and turn them into an auditory signal that is supplied to earphones being worn by the subject. Okay. Obviously, the nice thing about this is it does not require any surgery. The users, again, have to learn how to interpret this auditory signal, which is actually corresponding to a visual signal in front of their body. They have to learn how to, quote unquote, see with their ears. How does this work? This works by creating a series of auditory metaphors. Just a moment, let me close the window here. That's better. Okay, so they create a series of auditory metaphors. We spent a lot of time in this course talking about visual metaphors. Here we have a visual signal that is translated into an auditory metaphor. So objects that are close to the user on their left side is translated into a sound feature that they hear from their left ear. Objects on the right are translated into some auditory signal they hear through their right ear. So if there's a lot of obstruction, or you're about to hit an object on the left with the left side of your body, you hear a loud sound in your left ear. Same thing with the right side. Brightness, so brighter colored objects are translated as volume. So bright things are louder and dark things are quieter. Pitch, high pitch and low pitch. High pitch is what's higher up in your visual scene, and low pitch are for objects that appear lower in the visual scene. We snap an image from the cameras once a second and translate that into a pulse of sound that they hear. So every second, the user is hearing a different stereoscopic sound at their ears. Okay. Unsighted subjects who wear this technology for a while, some of them have repeated that they start to see a grayscale image form in their head. Kind of interesting, an amazing demonstration of how adaptive our brains are. We're gonna do our best. I'm gonna do my best to give you a sense of what this is like. What we're going to do is, in a moment, I'm going to play this video and I'm going to ask you to close your eyes, and you are not going to see this video, you're going to hear this video. This video is going to take a scene like you see here. In this case, there are three objects, and it is going to translate this into a sound that you'll hear. And obviously, there's a number of disadvantages here. The first one is that we don't have stereoscopic sound here, so this is just going to be the same sound for both ears. So it's not perfect. What's going to happen at each second in this video, we're going to swap in and out a different subset of objects. So at 1 second, there's going to be 3 objects. At the next second, there's going to be 5 objects. Then there's going to be 2 objects, 4, 5, and so on. I want you to see, given this description, if you know which is which. So you're going to hear these bursts of sound. For each burst of sound, can you tell how many objects are present? Got it? Okay, here we go. So please close your eyes. 3, 2, 1, here we go. Okay, you can open your eyes. Could you tell? Should we try it one more time? Okay, I'm going to play the same video again. Close your eyes, and I want you to think, when you hear a sound, how many objects are in the video at that time. Go ahead. Okay, please type into chat. You can open your eyes. Please type into chat yes or no if you think you had a good idea, if you were confident about how many objects were in the scene or not at any given time. Okay. All right, you can leave your eyes open. I'm going to play the video for you, and let's see how well you did. One more time. Okay, I have seen this video hundreds and hundreds of times. I've tried it with my eyes open, my eyes closed. I can't figure it out. The point here is to demonstrate how non-intuitive this is. It's very difficult for the front part of your brain, the rational part, to think your way through it. This is something that presumably just happens through large amounts of practice. Another great example of how adaptive the human brain is. Okay. We just looked at cochlear implants. Here's an example of a retinal implant, a retinal prosthetic. So this one assumes non-functional eyes. So the eyes aren't working, but the optic nerve, which you can just see here connected to the back of the eye. The optic nerve goes from the back of your eyes to the back of your brain, and at the very back of your head, that's where visual processing occurs. If the optic nerve is functioning, in the case of the retinal prosthetic, again, the subject wears these glasses, and the glasses have a camera. The camera catches what the user would have seen, and again translates that into an electrode array, and those electrodes electrically stimulate the optic nerve, and that electrical stimulation flows along the optic nerve into the brain. Back in 2003 was the first demonstration of this technology. It was funded by the U.S. National Science Foundation. You can go and read about the initial attempt back in 2003. At that time, they could only surgically implant 25 electrodes, so a 5 by 5 pixel array, not very high resolution. They succeeded in implanting a 25 by 25 array by 2010, so this is actually 10 years ago already, almost 20 years ago. They're up to a pretty high resolution at this point. The first retinal implant of this type was given U.S. market approval in February 2013. Again, the United Kingdom tends to be a little bit, have easier regulation with this. The first bionic eye implant was actually performed in the UK in 2015, and here's an example of one of those early successes.
This is what the world looks like to Ray Flynn. His central sight is gone, and he relies entirely on his...
Should I turn on the closed captioning here? Maybe that's better.
This is what the world looks like to Ray Flynn. His central sight is gone, and he relies entirely on his peripheral vision. Ray told me it severely limits what he can do. Hi, Ray.
I can't use the cash machines. I'd like to be able to go shopping and finding things and doing my own PIN number in the bill, but my brother has to do all that. He does everything.
I'm going to look at the back of your eye.
Ray has dry, age-related macular degeneration, AMD, which affects mainly the elderly and happens when cells in part of the retina become damaged. A few hours later, the surgical team at Manchester Royal Eye Hospital are ready to wrap this, the retinal implant, around the back of Ray's right eye, a world first for his condition. Age-related macular degeneration is the most common cause of sight loss in the developed world. At least 500,000 people in the UK are affected, so there is vast potential for any technology which can improve visual function and enhance quality of life. This is how it works. The patient wears special glasses which have a built-in video camera. The visual information is wirelessly transmitted to the retinal implant on the eye. Electrodes stimulate the retina's remaining cells to send those visual signals to the brain to interpret. 2 weeks after surgery, the key moment as the bionic eye is switched on.
So please close your eyes.
Ray is asked to keep his eyes closed during the test so the team can be sure whatever he sees must come from the implant relaying information from the camera on his glasses.
Diagonal.
Success.
Vertical. Horizontal. Oh, it was wonderful with my eyes closed to see the bars on there. It was really good.
For his surgeon, it's highly significant.
This provides hope to patients with not only this condition, but also to other patients with loss of central vision due to degenerative diseases. So this is just the beginning, and this could be the beginning of a new era.
Implants can't deliver fine visual detail like a human eye, but the technology is improving, and trials like this are crucial to the development of bionic sight. Fergus Walsh, BBC News, Manchester.
Okay, very exciting technology, obviously. In this case, we're looking at, again, these cybernetic prosthetics, which are bypassing non-functional sense organs like eyes or ears, but they still assume that the sensory nerves are still there. So the optic nerve, the auditory nerve. What happens if the optic nerve or the auditory nerve are also damaged? Can we supply signals from the external world directly to the parts of the brain that process signals that normally come from those sense organs? That's brain-computer interaction. Interestingly, brain-computer interaction is also just as old as the retinal and cochlear implants. Arguably the first example of this dates back to 2002. Again, in this technology, cameras are embedded in glasses that the subject wears. They communicate with signal processors that are implanted, in this case, in the visual cortex. Again, they are implanted directly in the back of the brain, which is the part of the brain that processes visual signals. If you're capturing signals directly from the world and bypassing the eyes and bypassing the optic nerve, what is it that the patient sees? Most patients report seeing phosphenes. So if on a very bright day outside you suddenly close your eyes, you'll see those floating blobs of bright light against the dark background of the inside of the lids of your eyes. That's what patients report seeing. So the patient is trained using the implant so that given a specific signal from the outside world, the patient reports where in their visual field they see a phosphene. So if, for example, we flash a flashlight on the right side of the human wearer and they report seeing a bright phosphene on the left, we alter the signal processor so that now the bright light out on the right side of their body produces a phosphene on the right side of their visual field. So like we've seen several times in this course, we're using machine learning to tune the translation from, in this case, a visual signal into electrical stimulation supplied to the visual cortex. And we're tuning that machine learning algorithm so that there is a closer one-to-one match between what's going on in the outside world and what the human subject reports that they see. Again, here's a very early video. I apologize for the quality of this video, but this is an attempt to try and show what a subject wearing or receiving this device sees.
Something right here. Right here. Right there. Okay. And right in front of me. Right in front of me. Now I passed him. Oh, now I got him. Now I got the blind. Okay, back to the blind. Little break. And the mannequin. Right here.
Okay, not perfect. You can sort of see these black and white dots that are meant to correspond to the phosphene seen by the subject. In the interest of time, I'm going to move on. You can go and watch this at your own leisure. This is an early CNN report of somebody with this technology actually driving a car. Pretty amazing. Okay. Here's another example of brain-computer interaction. Sorry about this. Let's get back to where we were. Another brain-computer interaction technology. In this case, you can see that the subject is wearing a cap, so there is no surgical implantation in this case. In this case, the cap is going to capture EEG, electroencephalography signals, EEG, which captures electrical activity from the surface of the brain. And they're going to be capturing information, particularly from the motor strip, which I mentioned before is the part of the brain that would be covered if you're wearing Bose headphones. By capturing signals from the motor strip, that is where ideas about how to move originate. So in this case, the subject is actually controlling a drone, as you can see here. And what they're asked to do is imagine moving their hands. So motor imagery of the hand. So if you sit quietly at the moment and you imagine raising your right hand above your head, but you do not do it, there is a particular part of your motor strip that is lighting up right now. If you continue to sit quietly and you imagine raising your left hand above your head, there is a different part of your motor strip that is lighting up, and that can be detected by an EEG cap like this. The signals that you get are sort of shown in the background of this figure here. You can read more about it in today's reading. You can imagine visually imagining moving your hand forward, back, left, right, tilting left and right with your hand. Imagine that your hand basically is the quadcopter. A KNN or some other machine learning algorithm can adapt that so the subject says, I'm now imagining moving my hand to the right, and whatever electrical pattern is produced in motor strip, that is translated into a signal that actually moves the quadcopter to the right. If the subject now says, I'm imagining moving my hand to the left, whatever different electrical signal is produced in that case, that is translated into particular signals that are sent to the quadcopter to actually move the quadcopter to the left. And by tuning this transformation from electrical signals in the motor strip to commands sent to the motors of the quadcopter, you can get to a point where the subject reports being able to think the quadcopter left, right, up, down, forward, and back. Okay. So let's talk a little bit about the motor strip. This is particularly important in brain-computer interaction. This is what the motor strip looks like. So imagine that we've taken a horizontal cut directly through the midsection of the brain. It turns out that if you start at the top of the head and walk towards the right ear, in this case, different parts of that motor strip correspond to different parts of the human body, arranged more or less from the bottom of the body towards the top of the body. This is known as the motor homunculus. So homunculus is sort of the Latin for the very small human inside your brain that's controlling things, which was kind of a silly idea for a long time, but it seems that that might actually be true in some regards. You'll notice that there's a drawing here of the human body, of the motor homunculus meant to represent this. You'll notice that certain parts of the body in this cartoon are bigger than others. Why do you think that's the case? What does that mean? What is that telling you about the motor homunculus? So you'll notice here's the hand down here. As I mentioned before, if you close your eyes and you imagine raising your left hand, Bryce says, how much of the strip is dedicated to that body part? Exactly. So as you know, obviously the palm of your hand is very sensitive. You'll notice that in the motor homunculus, the back is actually very small because your back is relatively insensitive. It's hard to locate, it's easy to locate on the palm exactly where someone is touching the palm. A little bit more difficult to localize down to a millimeter where someone is touching you on your back. You'll notice the genitals down here, which as you could imagine if they were drawn would take up a fair bit of this image. Okay. The motor homunculus is organized in a contralateral configuration. We've seen that word before. Anybody remember what it means? Or if your Latin's good enough, you should be able to parse this directly. What does contralateral mean? And what do you think it means in the case of the motor homunculus? There's a pretty strong hint at the bottom of the slide here. So we saw contralateral before when we were discussing Bradenberg vehicles, contra meaning across and lateral the line, across the line. So if you imagine raising your right hand, it's the left motor homunculus the left hand in the left motor homunculus that lights up. If instead you sit quietly and you imagine moving your left hand, it's the right part of your right motor homunculus that lights up. So it's actually pretty easy, and this was very surprising when this was first discovered. It's actually relatively easy if you're able to scan electrical activity from the motor strip to know what actions someone is thinking about. Pretty interesting. Okay. Here's another example. So in this case, they are implanting. This is not a cochlear implant. This is not a retinal implant. This is a motor implant or a motor prosthetic. They're going to implant a sensing device directly in the motor strip.
Study participants will undergo a surgical procedure where a small sensor is placed on the area of the brain responsible for movement. This sensor is connected to a pedestal that is attached to the skull and protrudes through the skin. The sensor records electrical signals from the brain, and these signals are fed into a device where they are interpreted by an operator using special software. From there, the signals are fed to a computer through which a study participant will attempt to control a cursor on a computer screen. The goal of the study is to evaluate the quality, type, and usefulness of cursor control that participants can achieve by using their thoughts.
Okay, so let's try and put ourselves in the shoes of somebody actually wearing or using this device. I want you to look at your screen, and I want you to imagine moving the cursor from the bottom of the screen to the top of the screen. Which parts of the motor strip do you think light up in that case? You're sitting quietly. You're not actually manipulating your computer to move your cursor from the bottom of your screen to the top of your screen. But if you're sitting there imagining that, which parts of the motor homunculus do you imagine are lit up in that case? It turns out that if you imagine moving a body part, and if you actually move a body part, it's a very similar signal. So if we go back to the bottom left example here, if you imagine moving your right hand and you actually move your right hand, you get very similar electrical stimulation from the motor strip. So for most of us, we move the cursor by moving our hands in the case of grabbing a mouse, or if you're using a mouse pad, moving the finger, which are signals that can be detected from the motor strip. Most of us are righties, so most of us, if you imagine moving the cursor on the screen, it is the left part of the left motor homunculus that lights up. The subject is imagining doing something with their right hand. What exactly they're doing is difficult to determine. So you get two very similar signals if you imagine moving the cursor up in the screen or moving the cursor down in the screen. Again, you can use a machine learning algorithm to learn which of those two actions the user is performing. Okay. Last video we're going to watch in the signal before we move on to part 2. In this case, we're going to look at a particular technology that is able to record not just from the motor strip, but as you can see in this video here, there are electrodes here that are capturing surface activity in the brain throughout the brain. Because what happens if you imagine something that happens outside the motor homunculus? If I ask you to move a cursor on the screen, then clearly the motor strip lights up. What happens if I show you an object on the screen and I ask you to imagine making that object more invisible? It's not exactly obvious what part of the motor strip, if at all, would be activated in such a case. So can we capture imaginal scenes, so things you imagine in your head, actions you imagine taking in the world, which may be physical actions, like manipulating a mouse to move a cursor, or moving your hand to move a quadcopter in three-dimensional space. But what happens if you imagine non-physical actions, like causing an object to disappear? Can a machine learning algorithm learn to do so? Let's have a look.
Up until now, our communication with machines has always been limited to conscious and direct forms. Whether it's something simple like turning on the lights with a switch, or even as complex as programming robotics, we have always had to give a command to a machine, or even a series of commands in order for it to do something for us. Communication between people, on the other hand, is far more complex and a lot more interesting because we take into account so much more than what is explicitly expressed. We observe facial expressions, body language, and we can intuit feelings and emotions from our dialogue with one another. This actually forms a large part of our decision-making process. Our vision is to introduce this whole new realm of human interaction into human-computer interaction, so that computers can understand not only what you direct it to do, but it can also respond to your facial expressions and emotional experiences. And what better way to do this than by interpreting the signals naturally produced by our brain, our Center for Control and Experience. Well, it sounds like a pretty good idea, but this task, as Bruno mentioned, isn't an easy one for two main reasons. First, the detection algorithms. Our brain is made up of billions of active neurons, around 170,000 kilometers of combined axon length. When these neurons interact, the chemical reaction emits an electrical impulse which can be measured. The majority of our functional brain is distributed over the outer surface layer of the brain, and to increase the area that's available for mental capacity, the brain's surface is highly folded. Now, this cortical folding presents a significant challenge for interpreting surface electrical impulses. Each individual's cortex is folded differently, very much like a fingerprint. So even though a signal may come from the same functional part of the brain, by the time the structure has been folded, its physical location is very different between individuals, even identical twins. There is no longer any consistency in the surface signals. Our breakthrough was to create an algorithm that unfolds the cortex so that we can map the signals closer to its source, and therefore making it capable of working across a mass population. The second challenge is the actual device for observing brainwaves. EEG measurements typically involve a hairnet with an array of sensors like the one that you can see here in the photo. A technician will put the electrodes onto the scalp using a conductive gel or paste, and usually after a procedure of preparing the scalp by light abrasion. Now, this is quite time-consuming and isn't the most comfortable process. And on top of that, these systems actually cost in the tens of thousands of dollars. So with that, I'd like to invite on stage Evan Grant, who was one of last year's speakers, who's kindly agreed to help me to demonstrate what we've been able to develop. So the device that you see is a 14-channel high-fidelity EEG acquisition system. It doesn't require any scalp preparation, no conductive gel or paste. It only takes a few minutes to put on and for the signals to settle. It's also wireless, so it gives you the freedom to move around. And compared to the tens of thousands of dollars for a traditional EEG system, this headset only costs a few $100s. Now onto the detection algorithms. So facial expressions, as I mentioned before, and emotional experiences are actually designed to work out of the box, with some sensitivity adjustments available for personalization. But with the limited time we have available, I'd like to show you the cognitive suite, which is the ability for you to basically move virtual objects with your mind. Now, Evan is new to this system, so what we have to do first is create a new profile for him. He's obviously not Joanne, so we'll add user, Evan. Okay. So the first thing we need to do with the cognitive suite is to start with training a neutral signal. So with neutral, there's nothing in particular that Evan needs to do. He just hangs out, is relaxed. And the idea is to establish a baseline or normal state for his brain, because every brain is different. It takes 8 seconds to do this. And now that that's done, we can choose a movement-based action. So Evan, choose something that you can visualize clearly in your mind.
Let's do pull.
Okay, so let's choose pull. So the idea here now is that Evan needs to imagine the object coming forward into the screen, and there's a progress bar that will scroll across the screen while he's doing that. The first time, nothing will happen because the system has no idea how he thinks about pull. But maintain that thought for the entire duration of the 8 seconds. So 1, 2, 3, go. Okay, so once we accept this, the cube is live. So let's see if Evan can actually try and imagine pulling. Oh, good job! That's really amazing. So we have a little bit of time available. So I'm going to ask Evan to do a really difficult task. And this one is difficult because it's all about being able to visualize something that doesn't exist in our physical world. And this is disappear. So what you want to do, at least with movement-based actions, we do that all the time, so you can visualize it. But with disappear, there's really no analogies. So Evan, what you want to do here is to imagine the cube slowly fading out, okay? Same sort of drill. So 1, 2, 3, go. Okay, let's try that. Oh my goodness, it's just too good. Let's try that again.
Losing concentration.
But we can see that it actually works, even though you can only hold it for a little bit of time. As I said, it's a very difficult process to imagine this. And the great thing about it is that we've only given the software one instance of how he thinks about disappear. As there is a machine learning algorithm in this. Thank you. That's all. Good job. Good job. Thank you, Evan. You're a wonderful, wonderful example of the technology. So, as you can see before, there is a leveling.
Okay, I think we're gonna pause there. So Evan obviously was the guinea pig in this case, and sorry, let me get back to the lecture here. Evan was the guinea pig in this case. There were 2 reasons that Evan was chosen to demonstrate this technology. You need to think very carefully about the physical, cultural, and physiological context of this technology. What were the 2 reasons? Why was Evan chosen to demonstrate this technology? As always in HCI, one reason is kind of obvious, the other one not so much. If you have an idea, go ahead and type it into chat. So already had data in the system. He has a very smooth brain. I hope he doesn't have a very smooth brain. That's never a very good thing. Evan actually hadn't used this system before. This was a live demonstration. The system had not been trained on Evan before. As you saw in this case, they did 2 different examples, and they collected training data just once for each of the 2 actions, and then testing after. Why was Evan chosen? Exactly. So the electrodes on the surface of his skull need to be pretty close to the skin, to the brain. What was the second reason? Anyone pick up on that? So the speaker here mentioned, as she was calling up Evan he's got a really smart, good brain, maybe. They tested mostly on males. That's a good question. I'm not sure. I think in this technology, at least as the way it was explained, is that it's only being trained on one person here, in this case, Evan. As Evan was being called up on screen, Ton mentioned that Evan had been a speaker at TED last year, speaking about something completely unrelated. Why does that matter? What's the physical or social context here that impinges on the ability of this technology to work? He's good in front of crowds. Why does that matter? He's comfortable on stage. Why does that matter? He doesn't get nervous on stage. What would happen if it was you up there on the TED stage being simultaneously watched by millions of people? If he's nervous, he messes it up. You can imagine if you've never given a TED Talk before and suddenly you're called up to be a part of a TED Talk. Not only are you part of a TED Talk, but you're part of a live demonstration which may or may not work, and it's up to you whether it works or not. You can imagine being extremely nervous at this point. And being nervous produces very large and strange, not strange, but far from baseline electrical patterns in the brain. Okay, we've got 4 minutes left, so I'm just going to introduce. I'm just going to introduce lecture 27. We clearly don't have time to go through it. Up until now, we've been looking at technologies that are implanted into the body, but they are physically connected to the body. What happens if we introduce interactive technologies, like robots, for example, into the body, that they are not physically connected with the body, but they are clearly part of our feedback loop with the world? These are micro-scale robot grippers. They are opening and closing in response to heat. And as you'll see in a moment, they can be controlled, they can be moved in a fluid through a magnetic signal. So there's a magnet there that is pulling the object. If you place a subject in a functional magnetic resonance imaging device, an fMRI, you can supply magnetic fields around and in the body. You might be able, with an external magnetic field, to direct a micro-robot to different parts of the body to, for example, deliver a drug or medication to a cancerous tumor. This is the most intimate form of human-computer interaction that is being considered at the current time. Okay, lots of other examples of this technology. Here's a digestible robot. We've run out of time, so I'm going to end with the following slide, which is the slide that I always end my classes with. Some of you are graduating at the end of the semester. Some of you will be staying on. You're all going to go off and do different things. This is not an HCI figure. This is an economic figure, which goes from 1963 up to 2008. So it's a little bit out of date, but it shows historical progression in basically, on the vertical axis, earning power. In the 1970s, there wasn't much of a difference between a high school dropout and someone who went to grad school, but clearly skilled labor and knowledge working is becoming increasingly economically valuable. So some of you may be considering whether to carry on with grad school or to enter industry. As you can see from my image here, even if you do go into industry, I invite you to come back to academia to pursue a graduate degree. Okay, so we've got 2 minutes left. Just a couple of closing remarks about the course. I hope you've enjoyed the course, learned a lot. Please remember to fill out the course evaluations. Those are important. I do read them, and I do try and take your advice to heart and improve the course for next year. Please remember on Monday to read through very carefully the final project document to make sure you know exactly what you need to submit and by when. If you present early on Tuesday morning, I know everyone is busy next week. Please do stay and watch all of the presentations. This is a form of respect to me and the TA and to your fellow students. So I hope to see all of you back here bright and early Tuesday morning at 7:30. We will meet here in the CS 228 teams. You have your final quiz due tonight. And I wish you a good rest of the week. I wish you good luck with your other final exams and projects and an uneventful end to the semester. Thanks very much, everyone. See you on Tuesday. Bye-bye.